So we have two equations to solve. We have the stream function equation, and we have the time-dependent vorticity equation. Let's first discuss the computation of the stream function. We're going to assume then that the vorticity is known, and we want to find the stream function. We need to convert this to a matrix equation and then use a direct method of solution using the backslash operator in MATLAB. So what we do is we apply natural ordering. I talked about this in my numerical methods class. So let's say we have a grid. So I will draw a grid here. Let's draw 3 lines. So this is our psi sub I direction. This is our theta sub j direction. So this is our grid. So natural ordering then orders the points on this grid in such that we go in this direction. And then we'll come around. And then we'll go this way, come around, and we'll go this direction. So we've ordered the points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and so on. Okay? What that means then is that we've taken our ij point on the grid and converted it to a single index k, which the conversion is that it's your I where you are in the horizontal line plus the j minus 1 where you are on the vertical line starting at j equals 1 times the number of points in the horizontal line, which is n, right? We have n points in psi and m points in theta. So we then convert this to a single index equation. To do that, it's easier to first define omega tilde of I comma j equal to this right-hand side, which is h squared e to the 2 psi I omega I j. I do that because this exponential factor only has an I index, so that will complicate the conversion. Okay, so once we do that, we can convert this equation. What do we have? Well, we have 4 psi sub k for this first term. This increments I by 1, so that becomes minus psi k plus 1. This term becomes minus psi k minus 1. But now we jump j by 1. So if we jump j by 1, we're jumping the index by n. So that becomes minus psi k plus n, and then minus psi k minus n. And then the right-hand side becomes our new variable omega tilde sub k. Okay, so this becomes our single index equation. This is, if we put psi now in a column vector, then this is a matrix A times our column vector psi using natural ordering is equal to our right-hand side B. So this is the equation we're going to solve computationally. This A then will have 4 going down the diagonal, a minus 1 and a minus 1, 1 above and 1 below the diagonal, a minus 1 n above the diagonal, and a minus 1 n below the diagonal. The right-hand side is this omega tilde. So this matrix A then is multiplying a column vector that is of length m times n. So this matrix A is m times n by m times m size. Very large matrix. So this is our solution for psi from the finite difference equation. but we have to treat boundary values differently. So we have to adjust this matrix A and this right-hand side B so that we enforce all of the boundary conditions when K lies on the boundaries. So that's the 4 sides of our grid. So this is true. We get the matrix from here, but we need to treat the boundary conditions separately. Separately. Okay? We need to enforce the boundary conditions in the matrix equation. So let me summarize. We have 2 equations to solve. One of them is the stream function equation. This is the discretized version. Previously, for the steady flow solution, we did iterative type of solutions. Now we're going to choose to do a direct solution of this equation. That means we need to write this equation as a matrix equation. We apply natural ordering so that we can stack the stream function into a column vector. Then this equation becomes a matrix times the column vector of the stream function equals the right-hand side. This matrix is large, mn by mn, but we can solve this basically by doing an LU decomposition of A one time and then using Gaussian elimination to solve A whenever B changes. So the vorticity will be evolving in time. This is the equation except for the boundary values when K lies on the boundary of the domain. Then we need to modify the matrix A so that this equation will enforce our boundary conditions. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.